If you're getting 8 hours of sleep, then you will have 16 hours left in your day, which you can divide between working and having time to do whatever you choose, or what we call leisure time. We can represent your options for how you will split your 16 hours on a graph like this one. A graph is just two number lines put together. The vertical axis represents the number of hours worked, and as you go up the vertical axis, you are increasing the numerical value of the number of hours worked, from 1 up to our maximum of 16. The horizontal axis represents the number of hours spent on leisure. As you go along the horizontal axis, you are increasing the numerical value of the number of hours spent on leisure from 1 up to our maximum of 16. We can plot some of the possible ways we can split our time. If we spend all 16 waking hours on work, we would have 0 left over for leisure. That would put us at this point on the graph. We're all the way up the vertical axis to our maximum of 16 hours. But since we have 0 hours left for leisure, we fall right on the vertical axis. If we make a change and shift 1 hour of work to leisure, we would be giving 15 hours to work and 1 hour to leisure, which would put us here. Notice that we moved down 1 step and over 1 step, representing that trade-off between working and leisure time. In fact, we can see that the opportunity cost of leisure is giving up the chance to work that additional hour and earn a wage. And if we want, we can keep making that trade-off, paying that opportunity cost. At this point, we're working 14 hours, leaving us 2 hours for leisure. And down across we can go, transferring our resource of time from one activity to the other. At this point, we're splitting our time evenly between work and leisure with 8 hours for each. But we can keep going, giving more of our time to leisure and less to work until we end up at 1 hour worked and 15 hours for leisure. Or even all the way to 0 hours worked with all 16 hours for leisure. Of course, there's even more possibilities than the ones we plotted here. Anything in between these points is an option, like working for 8 hours and 15 minutes and having 7 hours and 45 minutes for leisure. This line represents all of those infinite possibilities. Because this line represents the full set of possibilities for how we can use our 16 hours, we call it the production possibilities frontier. It's the frontier because we're unable to obtain any outcome beyond this line. If you think about it, anything below or on this line is attainable. You could split your time evenly, working for 8 hours and having 8 hours for leisure, which would be right on our line. But you could also spend 5 hours working, have 5 hours for leisure time, and then spend the other 6 hours just staring at a wall or something. That wouldn't be advisable because it wouldn't really be an efficient use of your time, but it is possible. What you can't do is work for 10 hours and still have 10 hours for leisure, at least given the constraint of only having 16 hours available. That would be unobtainable. And if we plotted it on the graph, it would be beyond our frontier. When it comes to how you use your time, we don't really think of it as production, though it is doing something with a resource you have, time. But generally, the production possibilities frontier is a model for thinking about the economy. The production possibilities frontier, or PPF, is a graph which displays the possible combinations of goods and services that can be produced by an economy given the resources and technology that they have. One of the basic questions an economy has to answer is, what will we produce? Do we want to produce X or Y? We can put that on a graph and consider every possible combination of X and Y our economy is capable of producing. Typically, when we draw the PPF, we draw it as a curve and not as a straight line like we did for our time. The trade-off between working and leisure time is constant. 1 hour of leisure means 1 less hour of work and vice versa. But not all trade-offs are constant like that. Instead, when it comes to production, we usually face the law of diminishing marginal returns, which is that as additional resources are allocated to the same purpose, the marginal benefit of those resources will decline. Imagine a traditional economy of hunters and gatherers. The hunters go off and catch fish, while the gatherers collect berries. Option A shows an outcome where the tribe is devoting almost all of its resources to fishing. The resources in this case are the time and effort of the people in the tribe. And in option A, the tribe has all its hunters working on catching fish, but also most of its gatherers working on catching fish. If they move to option B, they will catch fewer fish, but they will collect a lot more berries because the first people to shift from catching fish to collecting berries will be the gatherers, the people who are better at gathering berries compared to catching fish. But if the tribe decides to go all the way to option C, it means they will have to get hunters to collect berries, rather than spending their time catching fish, which is what they are good at. The trade-off is a lot bigger. Going from A to B, we can see in the chart that we lost 5 fish, but gained 5 berries. However, going from B to C, we had to give up 10 fish to get 5 more berries. The opportunity cost of berries is rising, and the reason is diminishing marginal returns. The law of diminishing marginal returns is that as additional resources are allocated to the same purpose, the marginal benefit of those resources will decline. What that means here is that as additional members of the tribe are allocated to collecting berries, the amount of berries the additional person will collect will be smaller. We should also think about points D and E. Point D lies below the PPF. On the chart, we can see that we get 10 fish and 8 berries. This is definitely obtainable, but it means some members of the tribe aren't pulling their weight. If everybody was working and doing their part, we could have more fish and more berries at option B with 15 fish and 10 berries. So while D is achievable, we can do it if that's what we want, it isn't efficient. Point E, on the other hand, just isn't attainable. Without more people in the tribe, catching 20 fish and still collecting 16 berries just isn't possible. So we call that point unobtainable. Efficiency is an important goal for an economy. We think of efficiency as satisfying 2 goals. Productive efficiency is the goal of using the least costly production techniques to produce goods and services. If we have hunters gathering berries while at the same time gatherers are catching fish, then we don't have productive efficiency, because swapping a hunter and a gatherer would increase both our fish and our berries by putting that person on the job they're better at. We want to use our resources as efficiently as possible. Only points directly on the production possibilities frontier meet the criteria of productive efficiency. So points A, B, and C have productive efficiency, because there's no way to get more berries without giving up some fish, and vice versa. But point D does not meet the criteria of productive efficiency, because we can increase the amount of both fish and berries we are producing. point E would be efficient, except that it is just unobtainable. If we could do it, we should, but we can't, so efficiency doesn't really apply. The other goal is allocative efficiency, which is when resources are used for producing the combination of goods and services most wanted by society. If the goal of this tribe is to produce the most food they can, then B is probably the best option for them and the one they will choose. But A and C could be allocatively efficient too if the tribe just loves fish or berries a lot more than the other. The key is that our choice between the options that meet productive efficiency will be determined by how our economic system tries to meet our needs and wants. And if that system is successful in that effort, the outcome will be allocatively efficient.